Welcome back to my DIY CNC router build. This is part 2 in a 4-part series on building this machine, and today we're going to be machining and building the Z-axis. In part 1 I covered the design and all of the components that I'm going to be using, and if you haven't seen that, the link will be in the description down below. In today's video we're actually going to get into a lot of machining and finally making some parts, but before that let's have a look at the design for the Z-axis. As I did with the rest of the machine, I actually initially designed this on paper. This was actually the first part of the machine that I designed. I first came up with the idea of building my own Z-axis as an upgrade for the X-Carve machine back in 2017, so it's been a long time in the making. In the last video I covered the general design requirements for the machine, and it's really important to still keep them in mind while designing the Z-axis. I still want it to be as cheap as possible. I've got to manufacture it all in-house, and I want it to be as stiff and accurate as I possibly can. However, on top of that, there are some specific design requirements just for the Z-axis that I've got to consider. First of all, I need the Z-axis to be as light as possible without sacrificing too much rigidity. This is because it needs to move around in the X and the Y direction, and if it's really heavy, it's going to have a really big inertia, which is going to make it hard to accelerate, and that means that the machine has to turn corners slower and stuff like that. A lighter weight Z-axis will be easier to accelerate, so then the machine can cut faster. The main way that I'm going to be saving weight is by using aluminium instead of steel for this part. Steel is typically 2.5 times more dense than aluminium, so it should save a lot of weight. My old X-Carve only had a travel distance of about 50mm, which I found often wasn't enough for me, so I want at least 100mm on this one. And finally, this one's quite important. I want it to be as compact as possible. If this Z-axis is really big and bulky, it's going to reduce the travel distance in the X-axis, and if it sticks out far from the X-axis plane, it's actually going to reduce the rigidity of the machine. The aim is to reduce the distance between the X-axis plane and the cutting axis of the spindle. As that distance becomes smaller, so does the moment from the cutting forces produced by the spindle, and therefore more rigidity in the machine. So in case that wasn't clear, the aim is to reduce this distance here. This is because moment equals force times distance, and the cutting forces is not going to change depending on how far out the spindle is. But you can reduce the distance, and hopefully you can see that by reducing the distance you also reduce the moment or the torque that's being applied to the X-axis. Here I've used a vertical cutting force as if I was drilling into a material, because it's easiest to draw in this diagram, but hopefully you can also see that it would be the same for horizontal cutting forces, which would be for milling. I reduced this distance by mounting the screw as low down as possible to reduce the profile of the Z-axis. You can see here in the cross section that I've made it as low profile as possible by making a cutout for the place where the screw goes in the middle. So that's all of the design considerations that I was thinking of while I designed the Z-axis. Now let's talk about parts. The only standard parts that I've bought are these 15mm linear rails. These were fairly cheap off eBay, and I'm not using the 20mm rails here because, as I said earlier, I'm trying to save weight and I'm trying to keep the profile low. I also got a standard cheap 300mm ball screw for the motion, and that's going to be connected to a NEMA 23 stepper motor via a timing belt. That's more than enough talk about the design. I think it's time to start cutting some chips. We're going to start by machining the backplate and the guides for the rails on a milling machine. These are both going to be made from pieces of extruded aluminium, so they're going to need machining flat first. If I'd made this from one solid piece, it would have saved drilling, tapping and counterboring all of the holes for the screws to hold these two different pieces together. However, I just had to use whatever material I had lying around. I started by flattening all of the larger edges using a fly cutter. Here I'm actually using a machine from one of the companies that I was working at a while ago, and this machine is much more accurate than the one I had at home, and it also had a DRO which made drilling and spacing the holes a lot easier. Unfortunately I couldn't do too much recording when I was here, just taking photos every now and again. Anyway, all of the operations for this were pretty standard. I faced everything off with a fly cutter to make it smooth, and I drilled and tapped loads and loads of N5 holes. Each hole had a marching clearance hole and counterbore in the backplate. These are spaced every 30mm to hopefully join these two pieces together as well as possible. To allow the ball nut to sit as low as possible on the Z-axis, I used a carbide insert cutter to remove some of the flange from it. I then put a deep 45° chamfer on the two edges of the pieces guiding the rail to make clearance for the edge of that ball nut. I then bolt the rail guides to the backplate from the back using all of those M5 holes that I made. Now that it's all one solid piece, I could then drill and tap the M4 holes for mounting the rails. Next it's time to look at mounting the ball screw to the backplate. Conveniently, the ball screw comes with these two mounting blocks, one for each end. I drilled and tapped some M5 holes vertically into the back plate so that I can mount the bearing blocks on like this. Here you can see why I had to remove material from the ball nut and chamfer the rail guides so that it can all fit together properly. Now back at home on my Centec manual milling machine, I then put two counterbores in the screw holes for the bottom bearing block. This means that the heads of the socket cap screw won't stick out below the bottom of the Z-axis. Then it looks like this once I mount the rails and get it all together. The next step is to make this back plate, which is going to attach the Z-axis onto the X-axis rails. I'm making this from some 10mm thick aluminium plate. I start off by drilling and counterboring holes for 16 M5 screws. These screws are going to allow me to attach the back plate onto the bearing blocks of the X-axis. Next, I used a 20mm end mill to face down a very shallow slot which almost exactly fits onto the Z-axis, so there should be no play once I bolt it together. I then drilled and tapped 8 M5 holes so that the Z-axis can be bolted onto the back plate. After that, I drilled and counterbored matching holes in the Z-axis itself for me to put the bolts through. So this is how the back plate attaches to the X-axis. I'll show how I made the X-axis in the next video. You can then see how the Z-axis fits very nicely into the very shallow slot that I made on the back plate, so it can slide up and down but still stay very vertical. The Z-axis then bolts onto the back plate like this. I actually drilled enough holes so that I'm able to shift the Z-axis down by one of the hole spacings, which is going to give me an extra 30mm of depth if I need to do something really deep. The Z-axis is slowly starting to come together and I think it's looking pretty nice. The next step is to cut down the linear rails to length so there's no overhang. So I slide the bearing blocks off the end of the rails and onto the plastic holders to keep the ball bearings inside. Then with the length of the rails roughly marked, I can try and start cutting them. I first tried with a hacksaw, but since they're case hardened, this didn't go very well. I then tried with one of those cheap carbide chop saws that can sort of cut some very thin box section, but this rail was way too hard and way too thick for it and it was making the blade wobble all over the place. I finally resorted to an angle grinder with a thin cut-off wheel and that made short work of the rails. I made sure to spray them with a bit of water so they didn't overheat and lose their heat treat right on the ends, not that it would really matter that much. Despite my best efforts, the cut left by the angle grinder was not square at all and it was really rough. So it was over to the milling machine again with a tungsten carbide tipped end mill to square off the end and make it completely smooth. I then used a Dremel with a very small carbide end mill to remove the burr around the edge and round off the edge so that I can easily slide on the bearing block. I can then reattach the rails and slide the bearing blocks back on and it looks so much better now that they're cut down to length. The next step is to make the motor mount to attach the NEMA 23 stepper motor to the ball screw via a timing belt. I'm going to attach this mount through the vertical holes on the bearing block. The first step was to make a spacer using this 4mm thick aluminium sheet. I still don't have a bandsaw, so I was doing this just with a hacksaw. Then it was over to the milling machine to clean up the edges and make everything square. My milling machine actually also has a horizontal attachment as well as a vertical one, and sometimes it's more useful to actually use the horizontal one, especially for holding thin sheet pieces in the vise like this. Here you can see how the spacer fits around the bearing block. The plan is to then bolt the motor on using this aluminium plate, which is actually from the original Z-axis that I had on my X-Carve machine. This would be a very simple part to make, but I'm not going to bother making a new one since I wanted to reuse as many X-Carve parts as I could. It just required a little bit of modification. I had to drill a few holes before I could fit it onto the new Z-axis. I wanted to use the front two holes of the bearing block to help attach the motor mount, but there wasn't enough room for me to put a nut on the other side. So I used an end mill to drill two quite deep counterbores into it, and then I inserted some threaded M5 sleeves that I made on my lathe. You can see that an M5 screw is easily able to screw into the hole now, and nothing sticks out the back. Now it's time to assemble the motor mount. First the bearing block goes in place holding the lead screw and the spacer goes on top. Then the motor mount can be bolted on top of that using the 2 screws going into the back plate and into the holes that we just made. I'm going to be connecting the motor to the lead screw using this HDT timing belt. There's a 1.5 to 1 reduction, so the motor should have enough torque to spin the lead screw. If not, I can always upgrade the motor. Once the belt is properly tensioned and aligned, it should provide very little backlash and very good rotational accuracy. Next is time to make the front plate. This is the piece that's going to bolt onto the linear rails themselves and connect the spindle to the Z-axis. This is going to be made from the same 10mm aluminium plate as the back plate. This stuff is already really flat, so I don't need to skim it flat on the mill. Again, I don't have a bandsaw, so I just had to cut everything with a hacksaw and then square it up on the mill. When squaring off fairly large pieces of plate like this, I found that the This Old Tony 2-piece vise that I made a while ago is so useful. It's by far one of the most useful attachments that I've made for my milling machine, and I'd really recommend that you check out his video if you haven't already seen it. This, combined with the fact that my mill can do horizontal milling, makes it really easy to square up large bits of plate. Once everything was squared off and deburred, I could then center punch some holes to attach the plate to the linear rails. I then drilled and countersunk all of those holes for some M4 screws. The next step is going to be to make something that's going to couple the ball screw nut to the moving plate, so the ball screw is able to drive the moving plate up and down. I'm going to make this from some aluminium round stock on my metal lathe. It's quite nice. This is actually some round stock that I cast back in 2016 in a video when I made my electric foundry, so it's really nice to reuse some stuff from an old project. The turning operations on this part were fairly simple. The first step was to turn the outer diameter to what I wanted. Then I drilled a hole in the back and then slowly used larger and larger drill bits until I was up to a 20mm drill bit. This is just big enough for me to fit my boring bar in, and then I could bore out the hole to the diameter of the nut on the ball screw. I was careful when reaching the final dimensions because I wanted to make this part a really close fit on the nut, so there's absolutely no play. So now I have this cylinder that fits really well over the nut, and you can then see where I need to remove material for clearance. Once I'd removed the excess material on the milling machine, you could see how well it fits around the nut. I could then mark some holes to be drilled and tapped for M5 screws that are going to bolt it onto the nut. I'm going to use 3 M5 socket head bolts to attach the moving plate to the nut coupler. These are again just drilled and countersunk in the exact same way as before. I then drill and tap 3 corresponding holes in the coupler itself. So I can put it all together and it's looking pretty good, apart from there's a 1.1mm gap between the nut coupler and the moving plate. This means that as you tighten down, it pulls really hard up on the lead screw and bends it slightly, and then completely jams everything together so you can't move it. So I need to make a spacer that's going to fill that gap. The space is too thin to hold in the vise, so I face off a piece of mild steel and superglue it to the top. This lets me access the entire face and flatten it down as thin as I want. Also, at this point in the build, I just bought a new camera and I've been saving up for this for 4 years now. It's a big investment for me, so I was really enjoying using some of the slow motion for that, and hopefully the videos from now on will be a lot higher quality. The superglue can be released with a bit of heat from the blowtorch. I use some 240 grit sandpaper on a surface plate to completely smooth out both of the faces and remove that final amount of material to make it the perfect thickness. This is what the spacer looks like when it's done, and I can insert it in between the nut and the moving plate and check that everything moves smoothly across the whole travel of the Z-axis without binding, and thankfully it does. It's all lined up perfectly. So now that I've got the ball screw coupled to the moving plate and everything moves smoothly without binding, it's a good time to test it under load and check that the NEMA 23 stepper motor has enough torque to spin the screw and move the axis. As I said in part 1 of the build, initially I'm going to be reusing the original power supply that I made for my X-Carve machine. I'm going to go into more detail on this power supply and Mark III setup on the computer in more detail in a future video. But for now I'm just going to connect it all and check everything works. And thankfully everything seems to be working fantastically. I can travel the whole length of the Z-axis without it binding up, and it all moves really smoothly. The next step is to make the holes to attach the spindle and spindle mount. Initially I'm going to be using this DeWalt 611 spindle which I was using on the last CNC machine. I know that this is pretty underpowered, and when I get onto milling metal I'm probably going to want to upgrade to a 3-phase VFD controlled water-cooled spindle, but for now this is going to do. Thankfully I can still use the original mount that came with the spindle, it just needs a little bit of modification. Attaching the spindle mount to the moving plate was simply a matter of drilling and tapping 4 M6 holes, and didn't take very long. And here you can see how all of these pieces that I've just made in this video attach onto the X-axis of the CNC machine. Again, I'm going to be showing how I make the X-axis and the rest of the machine in a future video. And that is pretty much it. Mechanically the Z-axis is now complete. Unfortunately right now it's the only axis that actually works, so I can't really do much with it apart from drill a few holes. But I'm really happy with the way that it's come out. It's incredibly stiff, and I can tell that once I get the machine working it's going to be really solid. If you enjoyed this video then make sure to check out the rest of the CNC build once it's uploaded. The link is in the description to the playlist with all of this build once it's done. I'm really sorry that it's been over 2.5 months since my last upload on this CNC machine. I really didn't want to rush it though, because I've been working on this project for over 2.5 years now and I wanted to get it as good as possible before I uploaded it, so thank you and your patience for waiting for this part to come out. You might have noticed that the machine isn't in my garage anymore, and in the last 2 months I've moved back down to university and brought the machine with me, which could be quite interesting once I get it running. It'd be funny to see what my landlord thinks about it. Anyway, I'm pretty confident that over the next couple of months I will find some time in between my university course and Corona to finish this CNC machine and upload some more videos on it. I want to say a massive thank you to all of my Patreons who help support this channel, and if you appreciate the amount of hard work and effort that I put into this video, then maybe you consider supporting me on Patreon as well.